All right. Hello, everyone. Um, so today, what I want to do is, again, I want to, like in previous lectures, I want to first go over chapter 3, the little bit of it that I think you may have questions on, and then talk a little bit about chapter 4, which is what we'll be finishing up this coming week. The next test is, or I shouldn't say the next, our first and only midterm is next Wednesday already. So not a bad time to start looking at the material. It goes quicker than you may think. So, but what I want to, first off, I want to do is I want to talk about the quiz. So let me just pull that up. So here we are, week 4. So here is our quiz. And so quite a few of you did well on it. Some of you did not as well as you probably would have liked. Again, the quizzes are a measuring tool. They help me assess how you guys are understanding the material, and also for you to assess how well you're understanding the material. Now I realize is that, I do a quiz on one problem, and that you might have missed one part of it, and doesn't necessarily mean you don't understand most of the material. So it's mainly, I try to select stuff that's kind of general to what we're covering. And at the end of the quarter, when I look back on grades, I really look not so much at quizzes, but I look more at the midterm and the final. So don't stress on the quizzes, I guess is what I'm trying to say. So any questions, though, about anything before I go into this? Okay. So remember that when we're doing a moment about a line,
keep like doing okay on the homeworks.
I can barely understand you. What'd you say?
Oh, it's nothing. I must have lagged out or something. I was just saying I do okay on the homeworks, then on the quizzes I like.
You're not. Well, that's. I would say is that again, the quiz is open notes. I try to take something on the quizzes that's kind of general, not sneaky. So that might be subject to debate. But for example, on this first quiz, the last one we did, I wanted to see if you guys could do a moment about a line. So I gave you the line AD, and then the tricky part on this was to figure out what the actual force was. That's why that was worth about half the quiz points, was figuring it out. And so I've kind of gone over it here. If you want to get FZX, FX, and FY. So we know that since the force is going in the negative Z direction, then sine 30 is going to represent the Z component of that force. And then the line here where my arrow is, that is a line that is in the same plane as the XY plane. So that becomes your horizontal projection, FH. So that's going to be just the 80 cosine 30. And then if we want to break that out, that becomes our hypotenuse to this line. So we know that the sine of that 40 degrees times that hypotenuse gives us our X component, and the cosine gives us our Y component. And then we just simply find a vector going from any point in the line to any point on the force. The easiest one is to go from D to C or from A to C. And so on the solutions that I posted, you can see that I did it both ways with either, and it turns out the same. So I would just pick the easiest one. So if we go from D to C, we have a vector that's just 250, 0, negative 200. And remember that R vector is not a unit vector, because the bigger the R vector, the bigger the magnitude of the moment. So you never want to divide that by its magnitude. And then of course we have the unit vector for the line. That's the one that you want to create the unit vector out of. All right. So the final answer for that was a scalar value of 7.25 Newton meters. And I don't know if it's hailing where you guys are. It's hailing quite hard in my backyard, if that's what you hopefully aren't hearing too much of that. Wow. Anyway, so that's that. So that's the quiz. Any questions on that?
So do you just put that into a 3x3 matrix? and then do it,
yes. Yeah, you would set it up though, but it's not a it's not a triple cross product though. That's the thing to remember. It's a mixed product. So it's 0.6 dotted with R cross F. So that's what you don't want to make the mistake of doing a triple matrix. So go ahead.
You cross your force with your displacement and then dot that with your line.
You cross you cross R cross F, always
right,
R cross F, right.
Right.
And then you dot that with your line. That's correct.
Sorry, yeah, got to get the order right.
That's okay. Yeah, it's important that you do. You don't want to miss that. So, but just if you just look at the solution, I did post it. It's up on Polylearn. If you look under, not Polylearn, I keep saying that, Canvas. Polylearn was our old platform. If you look on Canvas under modules, you'll see it. It's where I put all the solutions to everything, the homework and the quizzes. And there's also some past exams. So I'd encourage you to look at those to get a sense of what the test might look like for the next quarter. I mean, in the next week. Okay, so let's go ahead. Chapter 3, essentially the basis of chapter 3 was that we talked about, or that you looked at since last week, were the force couple systems, the equivalent couples, and equivalent systems. And so the force couple systems are pretty easy if you just have a simple force and a simple distance, but they can be more tricky. And I want to do an example one quickly that I gave on an exam, because even though it was a straightforward force couple system, it had a few things to it that you want to make sure you can do. Equivalent couples, those are just adding moments together like vectors. And then I'd say the equivalent systems, that would be like the last problem on the homework, where you have the platform, where you have, or the example that I had in the lecture, where you have the children standing on the raft, where you're taking the forces that each of them weighs and replacing it with a single force at a single location that's equivalent to the distributed forces that they create. Okay. So this problem here, now in this one, you have this, there we go. You have this robot arm, and it's a little different is that this has what's called a wrench attached to it. Now, a wrench is a force and a moment, and we really didn't talk about those. And so, but it's not necessary to understand. I mean, it's not necessary to understand their specifics to do this problem, because the difference with this problem is that normally when we say replace the force with an equivalent force couple system, we just have a single force. We move it to a new point and call it good. The only difference with this one is now we have an extra moment that we have to deal with. But doing that, it's not really that much different. You just want to make sure that you account for that moment when you add it to the final moment that you create. Okay, so that's the diagram. So let me switch back to my document camera. Yeah. All right. So this is a drawing I made of it, what it looks like. So here you have your X, Y, Z axis. You have the fifth. This is the end, and this is the important part that we want to know. The drawing. So there's our O, and there's D down here at this end. And in the original picture, I'm assuming, and it's not clear from the original problem. So what I'm saying is the 4.2 distance here in feet, that is going to be to this point here. All right. And we have to define it in order to do the problem. So I'm just going to define it to be to there. We know that this is 2.8 feet from here up. And we have a force of 9.8 pounds and a free moment of 52 foot-pounds. All right. So we want to essentially move this to that O, to point O. And when we say move it to there, what we're really saying is what force and moment has to be felt at O so that this overall system components have not changed. All right, so how do we do this? Well, the first thing we know is that we know that a moment about O is going to be equal to R D relative to O, right? Because we're going to go from O to D, and that's going to be crossed with whatever this force is. But we also have to add to it this moment. So we're going to just put out here in space plus the 52 foot-pounds. All right. And we won't worry about that for now, but we just need to acknowledge it. So let's approach this now just like a typical force equivalent system and not worry about this. So if we do that, we want to, first off, we have to figure out what is this 9.8 pounds. We see where it's going, but what is it in terms of a vector? So if we do that, we can say that, well, if this is our drawing, we can see easily that this, in this angle here is 30 degrees, that FZ is just going to be 9.8 cosine 30 degrees. So that makes life easy. So we'll say FZ is 9.8 cosine 30. And that gives me a value of 8.49 pounds. All right. Now, I generally don't like to see these equals like stacked like that. I'm doing it here to save space, but typically you should probably put it like this and say equals 8.49. I'm doing it here because I want to make sure everything's kind of stays consolidated. So then we know that our horizontal projection is just going to be down here. So we know that's just equal to 9.8 sine 30, or basically half of that. And that gives us just a 4.90 pound. And then we can subsequently, what we can subsequently do is we can say Fx and Fy, and they're just going to equal 4.90 sine 40. Because now we're relating them to this triangle up here, and 4.90 negative, because they're going in the negative y direction, cosine 40. Gives us 3.15 and negative 3.75. So my force, I'll just call F dc, because that's the direction it's going, is equal to 3.15 I minus 3.75 J plus 8.49 K. So really that's part of the problem, right? I mean, that's part of the answer. You want to always have in a force coupled system, you always have a force. So this is one of your answers that you of course want to box at the end. We're still going to do more stuff with that. So now one of the things that's in this problem is, remember that we have this, going back up here, we have this 52 foot-pound force, okay? Now, in order to add that, because eventually when we do moment about O, we're going to end up with a vector, right? So how do we add 52 foot-pound scalar to MO? Well, we have to convert this to a scalar. I'm sorry, not scalar. We have to convert this to a vector. So, well, we know that this is the direction. FDC is the direction of the force, but that's also the same direction as DC. So the nice thing is you can create a unit vector, lambda DC, just using this in the magnitude. So lambda DC is just 3.15 over the magnitude 9.8 pi minus 3.75 over 9.8 J plus 8.49 over 9.8 K. And there we have our unit vector. So what we can do then is we can take this 52 foot-pounds up here, multiply it by the unit vector, and that will give us this moment in IJK, which we can then subsequently add when we get to this point. That make sense to everybody? Any questions? All right, good. Okay, so I'll try to bring that sheet back. But so now we want to do, so we know then, let's go ahead and just make that vector MD, we'll call it MD, and that's just going to be 52, and then times lambda DC, right? And so if I multiply that through by this, okay, I'm just going to write out the answer since you guys, I know you can multiply through. It ends up being 16.69 I minus 19.90 J plus 45.1 K foot-pound. So we'll put that, we'll leave that for now. That's our MD. And now let's figure out our moment about O. So moment about O, our D relative to O, crossed with our FDC. So D relative to O ends up being, if we want, we need that because we have DC. So our, make sure I'm on the screen, you guys can see me. Go ahead and shout out if you can't see it or if I'm going too fast. So our D relative to O, if we go back and look at this diagram, then we know that we're going to go in the X direction, we're going to go out 4.2, but we're going on this side of the triangle, right? So that's the hypotenuse over here, the 4.2. So in the Y direction, it's going to be 4.2 times cosine 40. In the X, it's going to be 4.2 sine 40. And then the height is just simply 2.8. So that's how I go from O to D. I go this way in the Y, that way in the X, that way in that, in the Z. So what I end up with is simply negative 4.2, because I'm going in the negative X direction, sine 40 I plus 4.2 cosine 40 J plus 2.8 K, or negative 2.70 I plus 3.22 J plus 2.8 K. All right, so then now I just have to do the matrix, set it up, negative 2.70, 3.22, 2.8, and then put in my force, 3.15, negative 3.75, 8.49. So there's R, D relative to O, F, C, D. So I know you guys can do the cross product. So when we do that, we end up with 37.8 I plus 31.7 J minus 0.018 K. Now, this is probably a rounding error. I bet if I had kept all my decimal places all the way through here, that would have been 0. So if you get a number that's 100 times smaller than the rest of the numbers, then you can pretty much say it's 0. So this becomes our moment O, but we also have to calculate back in the moment D, and then that'll give us our moment total. So that's why we had to then, remember, we converted it using that unit vector. And so if we bring that back down, we have 16.69, negative 19.90, and plus 45.1 IJK. So we add them together, get a 54.5 I plus 11.80 J plus 45.1 K. And so that then is your answer in foot-pounds. So that and this, these two are what you want to see in the final answer. All right. So you can see that that's pretty much a garden variety force couple system. it's not super hard. It's not super easy, but you know, but if you understand the concept, you should be able to solve that. So, any questions? All right. Well, this week I remember to record the lecture, so you can go back and watch it. If you're bored on Friday night, got nothing else to do, you always queue up one of my lectures, and what better way to spend the evening? Get a bowl of popcorn. I wouldn't say crack a beer because we don't want to advocate that, but all right. So let's go on. All right, so week 4, what we're doing in week 4 is we have equilibrium in 2D. Sorry about that. Let me share a screen. So we're going to talk about equilibrium in 2D. Now, you should have already done a few problems in 2D or seen them in the lecture for today if you haven't looked at it yet. And at the end of last week, I introduced it. So it shouldn't be a completely foreign concept. And then in 3D, free body diagrams is the emphasis, because that's where it really, really gets important that you get everything written down. And then a lot of with solving 3D equilibrium, this is kind of a bullet point of how to do it. And I'll show you an example, but you want to identify all your force vectors. Then you want to take a moment about the point with the most unknowns, solve for the unknown tensions, and then some forces to solve for unknown reactions. Now, that sounds very trivial, I understand. But no, it's once you do a few, it'll make sense. But the idea, the big difference with chapter 4 compared to earlier is that we've been looking at resultants. So we'd say sum the moments about this point, and then that would be it. And you'd find a net moment. But we never set everything equal to 0. Only on a few problems have we done that. That's really what we're going to do in this chapter. But let's look at an example in 2D. Now, so in this one, you have a uniform smooth rod. And whenever you see the words uniform and smooth, that means there's no friction. And we won't deal with friction until chapter 8, but in general, in the future or on a final, anytime you see smooth, that means there's no friction. And it's subjected to the forces shown. You want to determine the reactions. So you see that there's these rollers. It's a roller C, roller B, and it's contacting one side or the other. Generally doesn't contact both. Okay. Now, for this chapter, I'd highly recommend is looking at the reaction types. Now, what do I mean by reaction types? Let me, we'll come back to this in a second, but I want to show you like what I mean by reaction type. So if we have an object, like say, the most restrictive reaction type is going to be where you have a pole in the ground. So if you have a pole in the ground, then it's essentially held and fixed in place. So if you put a force here, up vertical or horizontal force, then this is going to have a reaction where it can also support a force in the X and the Y. Or if we try to bend it from side to side, it's also going to support a moment. And so when you have a free body diagram that involves a pole that's attached to the ground, you have to write these in: the moment about A, AY, AX, assuming this is point A. And so the difference with that is you might have another situation where you just have a pole. It's like, let's say it's a ladder. And here's a wall, and you have a ladder resting against, it's a horrible ladder, but you have a ladder resting against the wall. And so in that case, if you assume there's no friction at all, which is kind of scary, then you'd have, this is point A and that's point B, then you just have AY and you just have BX. But the important thing is to recognize if you do have friction or not. So if in this case you did have friction, then let's say there's a mass. So let's say there's a certain weight on it, you draw that there, mg. So if no friction, that would be your complete free body diagram. If there is friction, then the tendency for this thing, a ladder, is to want to go like this, right? It's not going to go like that, it's going like that. So you would then draw your AY that way. And let's say there's only friction on this part of it, the wall is smooth, then you would just leave that as it is, okay? So anytime you have something that's attached or resting on a surface, it's always the perpendicular force that contacts it. So another idea with this is, like, say you have a cylinder, like inside of a cylinder, and here, and so this is like so this has the ability to slide this way or slide that way. So in this case, if you're trying to figure out the reaction type of this, then it's really just going to consist of something that is perpendicular to the direction of travel. Because if this is free to slide either way, then it can't support a force in either direction. It can only support a force that way. So these are the kind of reaction types that you'll be looking at throughout this chapter. And they're summarized, I believe, on page 172 or 173. I might be getting that wrong, but in early chapter 4, they're summarized. And just look at them because you want to become familiar with them. Of course, you'll have your notes in your book for the test, but if you can recognize them right away, it's all the better for you. Okay, so getting back to our example. And what you can see with this is, so here's our example, and now there's the free body diagram for it. So you'll notice that they've labeled the 300 newtons. We've labeled CY prime, BY prime, and it just called it that because we have an alternate coordinate axis that's 30 degrees offset from the original. And we've labeled AX because it's against the smooth wall. Now you might ask, well, how do we know it's contacting the wheels on the bottom? Why aren't they contacting the wheels on the top? Well, we don't know that. So if you think about this logically, I would suspect that perhaps the C is being contacted on the wheel over here, and probably B is being contacted here. But we don't know that for sure. So we're basically taking a guess, but it's okay because if we're wrong, it'll come out in the math when we do the problem. So let's do that problem. I'll show you what that means. Okay, so here's my drawing that looks like it. So I have my 300 newtons, 2 meters, 4 meters, 2 meters, CY, BY, AX, and then the 4,000 Newton meter. Okay, so whenever you have 2D equilibrium, then your forces, or your equations that you have are summing the forces in the X to 0, summing your forces to Y to 0, or summing the moments about a point to 0. So those are your three equations. So we have 1, 2, 3 unknowns. We have three equations, so we can solve it. So this is statically determinate. And we'll talk more about that as we progress. There are things called statically indeterminate where you have more unknowns than you have equations for. So let's first look at this simply by sum of the forces in the X to 0. All right. So we know that this and this, that's 30 degrees. Sorry, it's kind of small, 30 degrees. So if I write that, I'm going to say CY prime sine 30 degrees. And that's this little leg of the triangle going this way. And then that's going to be plus BY prime sine 30 minus AX equals 0. Can't do much with that, three unknowns. So let's look at our sum of the forces in the y, 0. So all we're doing is taking the stuff that we already know and just applying it. So if we do that, we know that we have negative 300. And again, the axis we're using is just our standard y-axis like this, whereas the y prime and that are, so you can think of that as y prime, x prime, and that's 30 degrees. So minus 300, and then we have plus cy cosine 30 plus by sine 30 equals 0. So I'll call that equation 1, call it equation 2, and then my last equation, I'm going to sum the moments about A.
All right, I have a question.
Sure.
Why is it by sine of 30? Should it be cosine of 30?
Oh, yeah, it is. Sorry, I was copying too quick. Thanks for catching that. There we go. Good. So sum of the moments about A. So what we get then is we get, now in this case, we can, it doesn't really, all we're looking for is the perpendicular distance times the force. So we know that by times this distance wants to create a rotation that way. So we're going to, but because it's clockwise, we know clockwise is negative. So we're going to say minus by, and then that's by prime. The prime is not really that important. That's just how I've labeled it, times 2 meters. And then same with minus cy prime, only now that's 6 meters away from A. And then plus 4,000 Newton meters, because we have that free moment in there. And then plus 300 cosine 30, because again, we're looking at this perpendicular distance, and that's going to be times 8 meters, and that'll equal 0. So that's my equation 3. So 3 equations, 3 unknowns. If I take equation 2 and 3, that isolates by and cy. So effectively what I get from that is actually, let's simplify equation 3 first. If I simplify equation 3, I get 2 by prime plus 6 cy prime equals 6,078. So that's equation 3. And if I take equation 2, I get root 3 over 2 by prime plus root 3 over 2 cy prime equals 300. So, you can either multiply through by something and subtract, however you want to do it, substitute. Most of your calculators should be able to do these, so I would encourage you to figure that out. If you have this, I don't need to see the work of how you got it. To get to this point, you can just say use calculator, and that's fine, since that's just algebra. So when we figure these out, we end up with by prime equals negative 1,000. And cy prime equals 1346. So this is significant because remember earlier I was saying that it seemed that given the way this is loading, just from a mechanical viewpoint, if this is pulling down like that and it wants to do this, it makes sense that this bar would really want to do a shape like that. So the reaction should be here and here. And that's what this is telling us, because we guess by is that way, but because we got a negative 1,000, it means it's really like this. It's on the other side. Now, when you do your problem, when you draw your free body diagram, the main thing you want to do is get the forces down. If it turns out that you were backwards with your force, don't go back and change the free body diagram, because the free body diagram is only to represent the forces that are present. And this still represents it. It just doesn't represent it in the correct direction. So your answer will show where it should be. So by is negative. So what we have to do now is we know that, but we don't know AX. So we take these two numbers and substitute them back into equation 1. But the important thing to remember there is that if this is negative, you have to put the negative into here. If you trade it to positive, this is going to come out incorrectly. So if I do that, I get 13. So if I look back at this equation, it's going to be cy prime. So 1346 times sine 30 degrees minus 1,000 times sine 30 equals AX. And we can see right away that this is going to come out positive because that's sine. That's basically that. It's going to be 1346 minus 1,000, or essentially half of that minus half of that.
Can you scooch up a bit?
Yeah, thanks. Sorry about that.
No.
Yeah, so 1346 times 0.5 minus 500, essentially. So it gives us AX is equal to 173. Now, 0.0. So the fact that it's positive means that it's the correct direction, which it really couldn't be anything else, but it shows us that. Now, if it wasn't physically impossible, if this was negative, then that would suggest that this line that we drew up here to AX was actually incorrect. And that can happen too, where there's not when it's a reaction against the wall, but maybe you guessed it the wrong way where it could have either direction. So by substituting back in the actual negative 1,000, though, you can determine that. So we know that AX is in the correct direction and CY was, but BY wasn't. All right. So that's a typical 2D equilibrium problem that you would see in the first part of chapter 4. Again, your main equations are these. And when we go to 3D, it really doesn't change any. It just changes as there's a few more steps, but the actual method of solving is exactly the same. Okay, we got about 10 minutes. So I probably won't be able to finish the last one, but I can at least introduce it. So any questions on anything? Does it make sense? Okay. All right, so let's go back to PowerPoint. So 3D, as I said, identify force vectors, take moment about a point with most unknowns, solve for unknowns, sum forces to solve for unknown reactions. Now, it sounds like a lot of gibberish when you first read it, but it does make sense as you follow it. So I know you guys, if you want to write this down, or just remember kind of the identifiers. You want to identify your force vectors. That just means if you have tensions, you're going to identify those as vectors. Then you're going to take a moment about a point with the most unknowns. And this is basically to isolate unknowns that you can't solve for directly. There's just too many of them. And then that allows you to solve for those unknown tensions. And then once you know those unknown tensions, you can go back and solve for the unknowns that you took the moment about, because now you have enough information. So here's our example. We have this, there's a rod. Wait, there we go. There's the actual instructions. You have this horizontal boom, and it's labeled OC. It's supported by a ball and a socket joint and the two cables going from A to D and C to E. And so, and you know that you assume that it's if you're not given a weight of the boom, you just assume it's weightless. And you know that it has this ball and socket joint. Now, ball and socket joint is another type of reaction type. And the characteristic of a ball and socket is that it can't support a moment, but it can support forces. So if you think of, for example, our pole, if we had a pole that was concreted or a beam that was cemented into the wall, it could support a moment in 3 dimensions. You could rotate the beam, you could try to bend it in the X, you could try to bend it in the Y, and so it can support it in 3 directions. With a ball and socket, it can't. It's free to move. So the only thing it has is an X, Y, and Z component. So if we go ahead and sorry about that. Just grab my paper. So let me go ahead and go back to show you the top cam. All right, here we go. Okay, so here is our drawing. Okay, and I don't have numbers on it. And given the limited time we have left, I want to show you how you would set this up. So we know that we have this, like I said, at O, you have a reaction OY, OX, and OZ. So this is the free body diagram, what it should look like. You don't necessarily have to have the directions of CE and AD in there, but you do need to represent where the forces are. So you know that force is going there, that force is going there. So when we're doing a problem like this, remember from our steps, the first thing that we said was draw the free body diagram, identify the force vectors. So what are the force vectors? Well, we can identify TAD. Sorry. We know that TAD is equal to the scalar value of AD, and that's what you're looking for, the scalar value, times lambda AD. And we know that TCE equals the scalar CE times the unit vector of CE. So if we go ahead and using the dimensions on the diagram, you know, we go from C to E and back here from D to A, or I'm sorry, A to D, then what we can do is we just write them out just like we did in chapter 2. So what we end up with in this case is for AD, we end up with 2.5I minus 3J plus 3K all over 4.924. And so that's our lambda AD, okay? So we do the same thing over here and we get our lambda CE and we get its value. So the point is that we end up with a tension AD vector that looks essentially like this. You have 0.5077 TAD I minus 0.6093 times TAD J plus 0.6093 TAD K. All right, so that's our vector TAD. All right, and we do the same thing with TCE, and we get the same. We do the same thing, get it. Okay. Now, interest of time, how are we going to solve these? So if we go ahead and we take a moment about the point O, notice how we get rid of these three unknowns. And that's why we want to do that. So what we do then is when we take a moment about O, we have to figure out, well, what is the R vector? So if we go from O to each point, right, we're going to go from O to the point where this force emanates, O to where this force emanates, and O to where that force emanates. So if we write those out, we have R A relative to O is equal to just 3J, right? Just 3 in the Y direction. And if we do the same thing to the B, R B relative to O, then we equals 5J. And then RC relative to O equals 6J. So we have those. So then we set up our sum the moments about O set to equal to 0. And that's where it's a little different than before, because now we're setting everything to 0. So we set it up as RA relative to O and TAD.
And
right?
you do that because you know it can't have a moment?
It's not that. It's that it has nothing to do with the type of reaction. It has to do with at any point in the system, all the moments have to add to 0 for it to be in equilibrium.
Oh, okay. Okay.
And so this is a convenient way to get rid of the 3 unknowns. So we could take a moment about any point in space. So we could take a moment about up here, but it wouldn't help us because we'd still have too many unknowns. So the reason we pick that point is it gets rid of those. So when we do that, we end up with R, A relative to O, T, A, D. So we go ahead and put in those components, right? It'd just be 0, 3, 0, and then the components of T, A, D. And then we'd say plus R, B relative to O. And then that would just be, we know the 8,000 is just, that would look like, we call that P. That would just be what, 0, 5, 0, and then 0, 0, negative 8,000. Sorry, spacing. And then plus, and then the last one, of course, would be R, C relative to O. And then that would be with the CE, which you would have found. Okay, so you set that all equal to 0. All right, then you go ahead and do all your cross products, and you end up with a bunch of IJK components everywhere. So once you have all that, just like you did in earlier chapters, you would then take that and you'd separate it out into I, J, and K. And you would go ahead and you would have enough information here to then solve for T, C, E, and tension AD, right? So you'd solve for those using that, just by separating into IJK. Once you had this, then you go back in and you make so now you know the scalar value. So now you know the IJK components of each of these vectors, don't you? So now you sum the forces in the X to 0. And for example, you would say, okay, well, I'm going to say the OX component plus the I component, some coefficient times TCE plus some coefficient times TAD, right? And I know that all of that all equals 0. So all the X forces have to equal 0. So then I can just plug that into here. I can solve for that. And then I do it for Y and Z and I get everything. So it's a lot of steps. It's a little tedious, but it's very doable. And once you do a couple of them, they're actually fairly straightforward. Any last questions? Sorry, that went a little quick. I guarantee you, if you look at the examples I did in lecture that's posted, and I go through it a lot slower and I show you every step. So if you go through a couple of those, I think they should be pretty easy. Chapter 4 is really not that hard. Chapter 4 is actually, if I were to plot the difficulty of the class, it's like this. It starts out easy, gets a little harder. This is difficulty versus time. And then it gets easy again, and then it goes like that. No, I'm just kidding. Don't do that. It just gets harder. All right. Well, that's it. We're out of time. If you have questions, now's the time to ask them. Anything, guys? Any last minute question?
Professor, I have a question about the midterm.
Yes.
So will it be held like in class, or will it be how the quizzes were, like we're allowed an hour on Canvas and we just do it there?
With the midterm, it's going to be a two-part midterm. One part will be what I call asynchronous, meaning you'll have a window of time of the whole day to do it, and the other part will be synchronous, where you'll actually do it live with me, and I'll be here to answer any questions.
Okay. Will there be more information coming out on that? Like,
oh, definitely. Yeah, definitely. Yeah, I'll be posting stuff soon about that. Yeah, but thanks for asking.
All right, cool. Thank you.
Okay. All right, you guys, have a good week. You have questions, shoot me an email or see me in office. All right. Thank you.
Thanks, Professor.
Thank you. Thanks.
You're welcome.
Thank you.
You're welcome.
Thank you, Professor.
You're welcome.